Okay, everybody, here we go. We're going to do a couple examples of horizontal projectiles here. All right, now remember that horizontal projectiles, these are projectiles that are launched at a perfectly horizontal velocity. All right, and we're going to see that as a key word in all of these examples. This is going to be important when we kind of mix them all together. So the first example that we're going to do together has to do with Super Mario running with a constant velocity off of a tall cliff. All right. And so he's going to be running down and basically falling off of the edge of this cliff. And we can draw a nice little picture here that'll help us understand this. We have our cliff, all right, and Mario is going to come and he's going to fly perfectly horizontal off. And then when he does that, he's going to go down in the shape of a parabola, all right. And so there are a few things that we can label in our picture here. First, we can label our velocity. This is going to be horizontal, and we know that this is a velocity of 10 meters per second. All right. We also know some other things. We know that the cliff is 3 meters tall. So that means the distance from here to here is 3 meters. Now, since this is vertical, this is a vertical displacement, so that's a delta y. And because he's going in the downward direction, so Mario's going to fly off and he's going to start falling down, we're going to call this a negative 3 meters. All right. Now the question is asking us to solve for the horizontal displacement. How far from the base of the cliff? So this is the base of the cliff right there. We want to know how far does he hit that Goomba below. All right, and so that's going to be our horizontal displacement. That's the horizontal distance that he's actually traveling there. Okay, so these are all the things that we know. And one of the things about these problems is that we see that there's a mixture of vertical things, y's, and horizontal things, x's. So what we want to do is we want to split these things apart. And we're going to start by splitting this velocity right up here at the top. Now, every velocity, since it's a vector, has two components. Our horizontal component, Vx, and our vertical component, Vy. Now I'm going to call this V initial in the y direction because this is our initial velocity as he flies off the cliff. All right. Now we know from earlier that horizontal velocities, like this 10 meters per second, have all of their velocity in the horizontal direction. So 10 meters per second is the horizontal velocity, and none of their velocity in the vertical direction, and so that's going to be 0 meters per second. And so we take that velocity, split it into its two components, and then we start thinking about what it is that we are given. All right, so I'm just going to draw a little separator here, and we're going to separate everything into vertical stuff. Vertical. I think I spelled that incorrectly with two I's. There you go. All right, I can't let that happen. I have to change it. All right, so vertical. All right, and so what do we know in the vertical direction here? First, we know that our initial vertical velocity, VIY, is equal to 0 meters per second. We also know in the vertical direction our vertical displacement, delta y. That's going to be our negative 3 meters. And one thing that we also always know in our vertical direction is our acceleration, negative 9.81 meters per second squared. All right. So that's givens in the vertical direction. I'm also going to do givens in the horizontal direction. So in the horizontal direction, the only thing that I know is that I have a horizontal velocity of 10 meters per second. But there's something else that we know here too. We know that in the horizontal direction, things always travel at a constant velocity. And so for the vertical direction, things are accelerating. We have 4 different equations that we can use for those. Those are all of our kinematics equations. But in the horizontal direction, we only have one equation. It's the constant velocity equation. V is delta x over delta t. All right? So in this direction, the horizontal displacement, delta x, is what we're actually looking for. That's the distance from the base of the cliff. But for us to be able to solve for that, we're going to need to know the amount of time that Mario is in the air. Well, that's a problem. I can't solve an equation with 2 unknowns and solve it for one of those 2 unknowns. I need another piece of information. So somehow I need to get that time. Well, that's where the vertical direction comes into play. We know that the time that it takes for Mario to fall this 3 meters, our vertical displacement, is the exact same amount of time as what it takes him to move left to right. So he can't be falling for a longer or shorter period of time than he's moving left to right. So those times have to be the same. So if I solve for it in the vertical direction, then I can use it over in the horizontal direction. And that's kind of the key to these problems. So if I look, the equation that I will use in my vertical direction, all right, is that we have displacement, initial velocity, time, and acceleration. So 1/2 AT squared. And so that's the equation that I'm going to use to solve for time. So if I substitute all my values, I get my -3 meters equal to 0 meters per second times t plus 1/2 times -9.81 meters per second squared times t squared. And if I solve this for t, notice that goes away because it's 0. All right, 0 times anything is 0. And I solve for time. And go ahead, you punch it into your calculators, I'll punch it into my calculators. We should end up with a time of 0.78 seconds. All right. So that time right here is the amount of time that it takes Mario to fall 3 meters. Well, that's the exact same amount of time that it takes Mario to move left to right through his displacement. So I can use this 0.78 seconds to solve over here for my horizontal displacement. So I'll use my 10 meters per second in my horizontal direction. I'm looking for displacement. I know my time is 0.78 seconds. If I go ahead and solve that, you punch it into your calculator, I punch it into my calculator, I get 7.8 meters. And so that's our first example. Here we're finding a horizontal displacement based on how long it takes for Mario to fall. All right, so there's example number 1. So we see that we kind of have a horizontal thing, we have a vertical thing. We keep all of our variables separated from each other. Horizontal things can't get mixed with vertical things, and vertical things can't get mixed with horizontal things. The only thing they share in common is the time. That's it. All right. So let's kind of move down. Now we have a gun that's firing a bullet. All right, I'm going to clear this. I'm going to clear this from the screen here. So I have a gun that fires a bullet horizontally, and it hits a target that's 50 meters away. During its trip, the bullet has a vertical drop of 6 centimeters. What is the muzzle speed of the gun? So looking at this one, I already see that it's a little bit different because we're looking for speed or velocity instead of a displacement. So it's going to have a little bit of a different solution here. So I'm going to start with a bullet firing, and I know as soon as I fire a bullet horizontally, that's going to come out and it's going to immediately start curving down. Now notice that's like a really drastic kind of curve that I'm showing, right? But drastic is good. It helps us see what's actually happening here. We know that the target is 50 meters away. And so that means 50 meters of distance in between the two. That's my horizontal displacement, 50 meters. And I also know that the bullet drops 6 centimeters in that time. So that is my vertical displacement, 6 centimeters in the downward direction, -0.06 meters. All right. And what we're looking for here is our velocity. Now, even though we don't know what that velocity is, we do know one of its components. We know that this velocity is horizontal. And if it's a horizontal velocity, then that must mean that the velocity in the y direction is 0 meters per second. So it must have a y component or a vertical component of 0 meters per second. The horizontal component is what we're looking for because that is the velocity that we're looking for. That's the fired or the muzzle speed of the gun. So we're going to go back to our vertical and horizontal stuff. All right. So I'll have my vertical and my horizontal. And I'll start listing everything that I know here. So in the vertical direction, I have an initial velocity of 0 meters per second. All right. I also know a displacement. Delta y is 0.06 meters. I also know my acceleration, negative 9.81 meters per second squared. Over here in the horizontal direction, I'm looking for my velocity in the x direction there. I know my horizontal displacement is 50 meters, but for me to be able to solve for that velocity, I'm also going to need to know how much time it was in the air there. So again, I'm going to use the vertical direction to solve for time, and then I'm going to use that over in the horizontal direction to solve for the velocity. All right, so I'm going to use that same equation again. How do I know that this is the one I'm going to use? It's got all of my givens and all of my unknowns in it. All right, so negative 0.06 meters. The initial is 0 times time, so I know that that's going to be 0. Okay, go ahead. Don't forget to square that, all right? And I go ahead and I solve for t. And I get a value of 0.11 seconds, all right? So 11/100ths of a second. Now I'm going to use that up here to solve for my velocity. Again, in the horizontal direction, it is a constant velocity, all right? So I'm always going to use that equation in the horizontal direction. So my horizontal velocity, I have my displacement of 50 meters, my time of 11/100ths of a second, and I get a velocity of 454.55 meters per second. And so there it is. This is the velocity that the bullet comes out of the gun with, all right? Because it's totally horizontal, the vertical component was 0, and the actual velocity there that it came out with was 454.55 meters per second. I solved for my time in my vertical and used it over my horizontal. I could just as easily do the opposite. If I had enough information in the horizontal direction, I could solve for time there and use it in the vertical if I needed to. So many different options. All right, so those are our 2 horizontal examples. Hopefully this helps you with your homework.